will see some examples of systems with a negative oxidation state. Let us consider this compound NaN3. This is called sodium azide. Sodium azide, AZIDE. Azo stands for nitrogen. Azide. Generally, negatively charged species, they have the suffix E. Azide, oxide, nitrate, chloride, sulfate. That is to be noted. But the same compound, you can see NH3. Here, nitrogen has positive oxidation state. You will see in the assignment of rules for oxidation number later. At present, we can see Na is more stable as Na plus. N we don't know. So, oxidation state can also be positive, negative, zero and even fraction. We can test. First, here let us calculate the oxidation state of nitrogen in the compound sodium azide. Sodium azide is having the formula NaN3. So, sodium loses one electron to form positive charge. So, its oxidation state is +1. Plus, there are 3 nitrogen atoms. Its oxidation state we have to find. Let it be X equal to 0. So, overall it is neutral molecule. We will once again revise the rules for the calculation of oxidation number bit later. Now, solving this equation, 3x plus 1 equal to 0 or 3x equal to minus 1. X equal to minus 1 by 3. Here the oxidation state of nitrogen is negative as well as fraction. Oxidation state of nitrogen is negative as well as fraction. Now let us calculate the oxidation state of chlorine in the compound hydrogen chloride. Hydrogen, so once again we call it as hydrogen chloride. Here we call it as azide. Whenever NaH, we call it as sodium hydride. Both the compounds contain hydrogen, but they are given different suffix. NaH is called sodium hydride, but this compound is called hydrogen chloride. There is one another compound ClO2. This compound is called chlorine oxide, chlorine dioxide. So whenever it has negative oxidation state, it takes the suffix, its name takes the suffix E. Oxide, nitrite, chloride, like that. But if it takes positive oxidation state or a 0, it can take the elemental name itself. Chlorine appears in both the compounds, but naming is different. Hydrogen chloride, chlorine dioxide. Hydrogen appears in both the compounds, naming is different. Sodium hydride, hydrogen chloride. In the case of sodium hydride, already we have seen +1 plus hydrogen X. If we solve, X equal to minus 1. X plus 1 equal to 0 or X equal to minus 1. Here hydrogen plus 1, chlorine we don't know, 1 plus X. Here chlorine oxidation state is minus 1. Oxidation state of chlorine is minus 1. But here chlorine oxidation state would be positive because we call this compound as chlorine dioxide. So chlorine dioxide we don't know. Oxidation state of chlorine, let it be X plus, there are 2 oxygen atoms, each having an oxidation state of -2 equal to 0 or X minus 4 equal to 0 or X equal to +4. So in some compounds chlorine shows positive oxidation state such as chlorine dioxide. In most compounds it shows the negative. So generally halogens show the negative oxidation state. Chloride, bromide, iodide, all halogens, their oxidation state is negative. Similarly, oxygen group elements, oxide, sulfide, selenide, telluride, these compounds negative oxidation state. Metals and alkali, first periodic table, we would have studied in the column periodic table, first 2 groups of metals, alkali metals, alkaline earth metals, their oxidation state is always plus. Alkali metal oxidation state is +1. Alkali metals are +2, like that. So oxidation state decreases from left to right in the periodic table. Here rightmost elements are halogens in periodic table, or halogens are most electronegative. halogens have negative oxidation state. Lastly, a question may arise with respect to inert gases. What is the oxidation state of inert gases? Because inert gases will not form any, hardly they form compound. Already the name is inert, means that they will not react with any other thing. Helium, oxidation state of helium is only 0 because it is not even a covalent compound. So helium 2 does not exist. So oxidation state of inert gases is 0. Oxidation state of electropositive metals is plus. Oxidation state of halogens and oxides are minus. So we can compare the oxidation state of nitrogen in different compounds. This is NaN3. Another compound, common compound is nitric acid, HNO3. Here we have seen nitrogen oxidation state is minus 1 by 3. Minus 1 by 3. Whereas in HNO3, let us calculate the oxidation state. So nitrogen shows the oxidation state of minus 1 by 3. Hydrogen 1, nitrogen we don't know, plus 3 oxygens are there, each having oxidation state of minus 2. Overall equation 1 plus x minus 6 equal to 0, or x minus 5 equal to 0, or x equal to plus 5. So nitrogen shows positive oxidation state, negative oxidation state, fractional oxidation state. So these are to be noted. These are some of the examples of different oxidation state. What we conclude from these studies is that oxidation state is different from valency. Now we are in the process of differentiating between the terms oxidation number and valency. Oxidation number can be positive or negative or 0 or even fraction, but valency is always positive integral value, that is to be noted. Valency is the system, because valency is the combining capacity. So it can combine with one atom or combine with two atoms, or it cannot combine with any atom. Valency of helium is 0, means that valency cannot, helium cannot combine with any other atom. Oxygen can combine with 2 atoms. Nitrogen can combine with 3 atoms, like that. But no element or atom will combine with the fractional atoms. So valency cannot be a fraction. So it may appear to be same. Oxidation number and valency terms may appear to be same, but they are carefully to be distinguished in the sense that oxidation number can be positive or negative or 0 or even fraction, but valency is always positive integral value. Now lastly, we will see the important rules to be followed in assessing the oxidation numbers of various elements in different compounds. Now rules for oxidation, rules for assignment of oxidation number. So we have seen the distinguishing aspect between oxidation number and valency. Now important rules for oxidation number assignment to particular element in a compound. So here the point to be noted, or in the case of oxidation number, these are the points to be noted. First, let us write briefly O dot N means oxidation number. Oxidation number of free elements. So oxidation number can be represented as ON for sake of convenience. So oxidation number of first one, free elements, is generally taken as 0. Free elements means helium, neon, argon. So free element, or even hydrogen in hydrogen molecule. What is the oxidation state of hydrogen in hydrogen molecule? Oxidation state of hydrogen in HCl is +1, we have just now seen. But oxidation state of hydrogen in hydrogen molecule is 0. So hydrogen in hydrogen molecule, sulfur in a compound called, there is sulfur 8 compound. There are 8 sulfur atoms. So we have studied about the property of catenation. In the catenation is the capacity to combine with similar atoms, same atoms, you will see. But for example, oxygen can catenate to combine with another oxygen to form oxygen molecule. Hydrogen can catenate or combine with other hydrogen atom to form. So this phenomenon is called catenation. So sulfur catenates 8 times. Sulfur combines with 7 other sulfur atoms to form a newer system called sulfur 8. It is a catenated system. Here also the oxidation state of sulfur is 0. So because we cannot assign 8x equal to 0, even if you put x equal to 0, you can get 8x equal to 0, x equal to 0. So oxidation number of free elements or elements in covalent compounds or elements in catenated species is taken as 0. That is the first rule to be followed. Second rule, oxidation number is generally charge on the particular species. Oxidation number is the charge on the species. Just now we have seen what is the same compound we can illustrate. What is the oxidation state of hydrogen in hydrogen chloride? Oxidation state of chlorine in hydrogen chloride. So hydrogen is taken as +1. Chlorine we don't know because chloride suffix it is negative. So 1 plus x equal to 0, x equal to -1. So H plus Cl minus, that is H plus +1 is the charge on hydrogen, -1 is the charge on chlorine. That is why oxidation number can also be viewed as the charge on the elements. Charge on the element. Third point, oxidation number of a full compound is 0. Oxidation number of a compound, because everywhere we equate only to 0. Oxidation number of a compound is taken as 0. But oxidation number of an ion is not taken as 0. For example, chromate ion Nital CrO4 2 minus, sulfate ion sulfate, here oxidation number let us calculate the oxidation state of sulfur in this sulfate ion sphere. It is viewed as X, assumed as X, plus there are 4 oxygen atoms, each has an oxidation state of -2. Total charge we got to equate, we should not equate to 0. So then it has to be solved. So oxidation number of a neutral compound or in any compound is 0. That is to be noted. Now the fourth rule is that regarding the oxidation number of fluorine in its compounds. Oxidation number of fluorine in all of its compounds is -1. If you take any fluorine compound, it is always called fluoride. HF, hydrogen fluoride. NaF, sodium fluoride. Because fluorine is the most electronegative element in the periodic table. It attracts electron from all other atoms excepting of course the inert gases. So fluorine oxidation state is mostly -1. Next point is about oxidation number of hydrogen. So already we have discussed, we are revising. Hydrogen can take oxidation state -1, 0 or +1 depending upon the compound. We have also seen examples. HCl, hydrogen shows the oxidation state of +1. Sodium hydride, it shows the oxidation state of -1. Hydrogen molecule, it shows the oxidation state of 0. So it depending upon the environment, its oxidation state varies. That is to be noted. Next, oxidation state of metals. Metals are divided into 2 types. Alkali metals, alkaline earth metals. First group metals excepting hydrogen, lithium onwards, lithium, sodium, potassium, all have the valency of +1. Oxidation state of +1 or valency of +1. In some cases, oxidation state and valency can match, but in every case it does not match. That is to be noted. So alkaline earth metals, calcium, magnesium, etc., their oxidation state is taken as +2. And metals are in the aluminum group, boron, aluminum, gallium, indium, thallium, etc., aluminum, the oxidation state is +3. So this about in general for metals, how many electrons it loses, hardly it will lose 3 electrons to a maximum. But it should not be confused with the oxidation state. In the case of potassium chromate, we have seen that chromium oxidation state is plus 6 or dichromate plus 6. It does not mean that chromium is a metal. Chromium will lose 6 electrons. Chromium cannot lose 6 electrons, or manganese cannot lose 7 electrons. As the this is only number of electrons transferred as a whole from one compound to other compound. So that is with respect to oxidation number of metals. Next, oxidation number of nitrogen. Oxidation number of nitrogen, it depends upon the element with which it is combined. If the element is more electronegative, oxidation number of nitrogen is positive. Generally, electronegative elements, oxidation state is also negative. Electropositive elements, oxidation state also positive. So alkali metals and alkaline earth metals, they are called said to be electropositive. So their oxidation state is plus. Halides, halogens, oxygen group, etc. they are electronegative elements. So their oxidation state is -1. But in this period, nitrogen comes in the middle. Nitrogen comes in the middle. So mostly it forms the compounds by sharing. In typical cases, it may lose or gain. So once again, number of electrons gained or lost cannot exceed 3 or 2 depending upon the case. Already nitrogen, we might have discussed about the electronic configuration. Nitrogen, once again to revise, nitrogen atomic number is 7. Outermost shell contains 5 electrons, inner shell contains 2 electrons. So out of 5 electrons, 3 is its valency. So 3 electrons are going for bonding, 2 electrons are said to be lone pair. So depending upon the environment, it may take positive oxidation state or negative oxidation state. If it is combined with more electronegative material, its oxidation state is +1. If it is combined with more electropositive material, its oxidation state is minus. Here we have seen the example. Anyhow, we will see the individual ones, Na3 and NO, whatever be the case. So here sodium +1, nitrogen we don't know, X. So let us calculate the oxidation state of nitrogen based on these rules. 3 into oxygen is -2. Oxygen is -2 equal to 0. So 1 plus X minus 6 equal to 0, or X minus 5 equal to 0, X equal to 5. So oxidation state of nitrogen in sodium nitrate is +5. But this is NaN3. This is NaNO3. This is NaN3. This we have already seen. +1 plus 3 nitrogens are there. X we don't know. 3x equal to -1. X equal to -1/3. That is to be noted. So here its oxidation state is -1/3. It is a covalent compound. Here the oxidation state of nitrogen in its free elements or compound is 0. That is to be noted. Now lastly, 4 more rules in the assignment of oxidation number. Next one is about the oxidation number of oxygen. Oxidation number of oxygen. So we have noted oxidation number as ON. So oxidation number of oxygen is generally -2. Generally means that there are some exceptions. Important exceptions are 2 compounds, OF2, peroxides, type of compounds called peroxides, third type of compounds called suboxides. Peroxides, suboxides. Here we have written OF2. So already we have to distinguish about water and OF2. Water can also be called as hydrogen oxide. Here oxygen comes. Water can also be, so water is nothing but hydrogen oxide. But here it should not be called as fluorine oxide. It has to be called as oxygen fluoride. Oxygen and fluorine adjacent elements. Both are noted for its electronegativity. Fluorine also electronegative. Oxygen also electronegative. Fluorine oxidation state is also minus, oxygen oxidation state is also minus, but there is a compound existing between similar minus oxidation state, negative oxidation state. This compound is called oxygen fluoride. Let us calculate. Oxygen, we have to assume X, plus there are two fluorine atoms, minus 1, so equal to 0, X minus 2 equal to 0 or X equal to 2. Here plus 2. Generally it is minus 2. Peroxide means, for example, hydrogen peroxide, H2O2. So here H2 hydrogen, we have seen that 1, 2 into 1 plus 2 into X equal to 0, 2X plus 2 equal to 0 or 2X equal to minus 2, X equal to minus 1. Here oxygen takes the oxidation state. Suboxide, there is a type of oxide called KO2. So in this KO2, K is plus 1 plus 2X equal to 0, 2X equal to minus 1, X equal to minus 1 by 2. So oxidation state is minus but lower value. That is why it is called this suboxide. So in some cases it is also called superoxides. Potassium superoxide, suboxide, superoxide. So the idea is that it can take any negative oxidation state. In a rigorous case, it can take also positive oxidation state. Generally, it is minus 2. Next is about halogens, which you have already discussed only for fluorine. For all halogens, it is minus 1. Fluoride, chloride, bromide, halide. So halogens oxidation state is minus 1 in the halides. But once again, there are some compounds called the interhalogen compounds. If you take this compound ICl, here this compound has to be called as iodine monochloride. So one another compound BrF3, it is called the interhalogen compound. Br is bromine is also halogen, fluorine also halogen. It is called bromine trifluoride. HBr is called hydrogen bromide. This is called bromine trifluoride. Hi is called hydrogen iodide. It is called iodine monochloride. So both are halogens. It has plus 1. This has minus 1. So this one. So you got to calculate. Iodine bromine X plus 3 into fluorine is minus 1. X minus 3 equal to 0 or X equal to 3. Bromine has the positive oxidation state of plus 3. Interhalogen compounds. So interhalogen compounds only it varies. So these two are given as combined rule. So oxidation state of halogen in interhalogen compounds. In interhalogen compounds. Compounds between two halogens. So interhalogens or interhalogen compounds. That is to be noted. Last one, oxidation state of metal. Metal, we have seen that oxidation state of metal. It is the number of electrons it loses or number of positive charge it forms. But metals are also supplied in the form of metal mercury alloys. Mercury is a quicksilver, it is also metal. This is called amalgams. AMALGAMs. Amalgams are nothing but metal mercury alloys. Mercury will diffuse into the empty spaces of the metal. So in such cases, if I write sodium amalgam is used as the reducing agent. Tin amalgam is used as the reducing agent. So sodium amalgam, sodium also metal, mercury also metal, tin amalgam, zinc amalgam, in all these cases all are metals. So you cannot assign both plus 1 or because metals we have seen positive oxidation state. If you assign oxidation state for positive for both, it will lead to chaotic result. So anywhere only in amalgams the oxidation state of metal is 0. So only in amalgams oxidation state of metals, tin amalgam, zinc amalgam, etc. Now another example for this, apart from amalgam, another type of compounds called metal carbonyls. Metal carbonyls. Metal carbonyl is a type of compound. For example, if I write NiCO4, it is called nickel carbonyl, FeCO5, iron carbonyl. So it is used, these compounds are used in metallurgy, metal purification. Metals are allowed to be reacted with carbon monoxide. They are forming metal carbonyls which is vaporized and it is recondensed to form the purer metal powder. Here in these compounds, once again, you should not carbon, it cannot be split as Fe5 plus and CO5 minus, not like that. It cannot split as Na4 plus and CO4CO minus. So in all these cases, oxidation state is only 0. It is a covalent compound. Because it is a metal compounds are generally ionic, but this is a covalent compound. So covalent compounds, in the covalent compounds, the oxidation state of metal is 0. So oxidation state of metal is generally number of electrons it loses to form ion, but two important cases in the formation of metal amalgams as well as metal carbonyl, the oxidation state is 0. So these points are to be noted in the calculation of oxidation number of a particular element in a compound. We have also seen that oxidation state can be negative or even fraction with some examples. So these are to be noted in calculating the oxidation number of certain elements. What is the significance of calculation of oxidation number? It predicts whether, from this we can predict whether a material can be used as oxidizing agent or reducing agent. We cannot generalize all the metals are used as oxidizing agent or all the metals are used, some metals are used as oxidizing agents, some metals are used as reducing agent. So the capacity is based on only on their oxidation number. So the significance of oxidation number and redox reactions we will see. Title is redox reaction. Redox reaction is only centered around oxidation number calculations. That is why it is a separate time is devoted to the identification or calculation of oxidation number of elements in different compounds. Last we will see the aspects of some more types of redox reactions.